Hello, I'm Mark Duffield, and welcome to the Semiconductor Design on AWS with guest speaker Qualcomm. Today I am super excited to be talking both about semiconductor, but also to hand this off shortly over to Anupama Asthana, who I've been working with for several years on their hybrid options and running AWS, I should say workloads on AWS. So super excited to be here. And again, just a overall welcome to reInvent, and even if it's virtual, we know it's going to be awesome. Contributors here, special call out here to Ian and Matt, who also did some contributions to this, and I'll let Anupama dive into that as well. Today what we're going to be covering is this, fairly short but very content rich. We're going to be covering AWS or semiconductor design. I'll then hand it off over to Anupama. And then at the end, I'm going to close with some resources for where you can go to actually figure out and how you can get help for running your workloads and your flows on AWS. All right, so with that said, we like to talk to customers about a fundamental rethink when they're thinking about transitioning over to AWS and thinking about pulling their workloads in from their on-prem data centers. So stop worrying about the capital expense, stop worrying about the capacity and technology options, but rather let's focus on innovation. Let's think about how you can actually have your engineers, your designers be thinking about the next big chip rather than worrying about the infrastructure details and worrying about, well, when is the next funding going to land and when is the next big technology going to land? We want to help you offload that and help you so you can actually be thinking about innovation rather than thinking about all of your infrastructure issues. And speaking of infrastructure, when you think about what AWS has and the capabilities that we have, this is just kind of a brief and terse list of what we have currently, right? So we have 24 launched regions, right? And each one of these regions has several availability zones. We also have 6 more announced regions on top of that, and a total of 77 availability zones. Additionally, we have 5 local zones, which are enabling ultra latency sensitive applications. And we're seeing a lot of customers in this space, in the semiconductor space specifically, really be interested in local zones and what can be done there as well. We're also spread out across 245 countries. We have over 97 direct connect locations. We have 220 points of presence, which are enabling things like Route 53 and S3 transfer and our CloudFront distribution, content distribution network as well with CloudFront. So if you look at the infrastructure of AWS, there's really not a place that we can't help customers, and we're continuing to build on that as well. So let's dive into semiconductor design on AWS. And this is just kind of a short and to the point idea that, an approach that we like to hand off to our customers, right? So you have the same things on the left side and the same things on the right, but now you're running all of this on AWS and we're helping you do that, right? So you're going to have the customer specifications, you're going to have the tools, the design data, project data, and the libraries that you're going to need to actually design a chip. That's all going to have the output of a next-gen connected device, whether that's an SoC or maybe it's just a small chip, maybe it's an ASIC, what have you. But the products are the same, right? So from wafer fabrication and assembled products, etc. And there's really not a workload in this space that we're not helping customers with, right? So from IP characterization and place and route and extraction and OPC, front end, back end, RTL, everything, we're doing it on AWS, which includes an entire SoC tape out. So when you think about running your workflows on AWS, we really like you to think about, well, let's not think about this as a completely different environment. Let's think about this as, well, maybe another data center that just might be had spun up in another location, right? We can help you transition these workloads off quickly to AWS, and it's going to look and feel much like it will on-prem. And with that, I'll hand it over to Anupama, who's going to deep dive into some of the architecture that they've been working on and some of the hybrid applications that they've been doing at Qualcomm. Anupama, over to you.
Thanks, Mark, for the introductions. I'm Anupama from Qualcomm, and I lead the grid solution engineering team for Qualcomm globally. And very excited to be here today and sharing our journey into AWS with the EDA workloads and some of the very creative innovations that came about as we went on this project along with the Amazon and Synopsys. So Qualcomm, just a brief introduction about Qualcomm and what we do here. Qualcomm is the world's leading wireless technology innovator. Qualcomm led the evolution of cellular roadmap, which has become increasingly complex over time. And as you all are already aware, wireless is a very dynamic industry. And it's amplified with the 5G foundation of industrial policy. And it's just driving a lot of revolution across multiple industries. And we are inventing and commercializing very critical enabling technologies in this space. What that means is we are fueling digital transformation across multiple industries, and it's expected to be 13 trillion of global economic impact until 2035. Some of the major industries we participate in are from healthcare to energy to manufacturing. 5G enables new cycle of innovation and leading to new business models, driving a lot of innovative design requirements from our engineering organizations globally. And what that means is we have to have very rich HPC platforms that are able to address the ever-increasing requirements of Qualcomm technology roadmaps and product offerings. Qualcomm has multiple data centers around the world, and how we manage that whole process of making sure we have enough compute capacity available in our data centers globally is through a very effective demand management process. So what we do is look at the product roadmaps, their consumptions over a historical timeline, augment the technology scaling factors, and come out with the output of global compute requirements that looks somewhat like the chart you see up there. As you can see, with the number of products that we are designing, their increasing complexity and changes in our technology nodes, we are driving a lot of compute requirements that comes in peaks and valleys because the tape outs are cyclic in nature. And it does create compute constraints from time to time. And how we want to augment our on-prem solutions is with this agile and flexible cloud offering that will enable us to basically give a very rich offering to engineering to be able to address unplanned workloads when possible, and also when there is the time to market is a constraint due to capacity constraint, we would like to address it with cloud offerings. So our vision is to enable flexibility in the engineering tapeouts during compute demand peaks by providing the ability for key workloads to be able to execute in the cloud. So the workload we picked was static timing analysis. With one reason, it is the most compute intensive workload in the design cycle, but it also comes with the challenge that it also happens to be the most complex workload in the design cycle. The benefit is, of course, the ability to offset our most complex CPU and memory intensive flow and enable peak shaving and provide the flexibility back to design teams in enhanced time to market capabilities. And the challenges are multifold, basically challenges in front of us was not only is a very complex flow, but it is also towards end of design cycle, very close to tape out. So any hiccups in the process would be um, very, I mean, that could impact basically your whole tape out cycle and customer deliverables. And there were multiple other areas that we needed to focus on to ensure the capability was introduced in a very complementary way to the engineering teams. In particular, we are talking about data needs, basically a process to generate specific bill of material for consuming specific to a single invocation of a workflow, and also migrating all of those potential data sources to the cloud within limited time notice, because when you need the compute, you really need it, and you do not have a lot of time to go invest in data transfers. The second area was basically the flow needs, which means the present flow manager software for physical design team had dependencies that required running on-prem and making sure that on-prem data was always in sync with the cloud instances. So there were make-based workflows that would expect local generation of some output files. So that complexity had to be comprehended in the hybrid cloud model. Also, there were concurrency needs. Basically, as you set up the hybrid cloud environment, any time delays in transition to the cloud, they should be compensated by access to a vast and highly performant compute in the cloud, because that's the motivator. In addition, there were adoption needs, which means transition to this completely new methodology and environment should be as transparent as possible for seamless integration with the engineering execution. So we worked on a rich architecture which is demonstrated on the screen there. On the left, you have basically your on-prem data centers with the data stores, your compute, and managed by a workload scheduling software. And then we connected that whole environment through encrypted VPN channels to AWS offering. And there we had our basic data replications done with very rich caching technology. And also we had a separate solution for reference data. So why we split the two is if you try and cache all the data, then you are dealing with terabytes and terabytes of data, which can be very time consuming. So intelligent partitioning between what is the active data set versus what is the reference data set was one key decision we made in our design process. So cache presentation allows near instantaneous peering at mount level, and we were able to achieve a speed of 1.99 gigabits per second transfer rate in the testing for the caching partitions. For the reference data, we chose to go with multi-threaded APIs to S3 and with the metadata manifest that allows you to present as POSIX file systems using Lustre. So this was useful because we could burn down the Lustre instances between the execution time of different workflows, making it very cost efficient. And also we were able to achieve a better speed of transfer, which was 2.92 gigabits per second. For making sure the flows were working well, we were forwarding our on-prem scheduler to cloud native scheduler and using basically remote execution protocols. So it was transferred into engineering community, and also cloud generated output files were being cached back on-prem to make it seamless from a workflow checkpointing and progression perspective. Also, we were able to ease the adoption into this new architecture by making sure the native workflow manager as well as the job submission methodologies did not change on engineering, so they were able to work as usual without major impact into adopting the hybrid cloud environment. So the results are basically shown as comparative runs on the screen there. If you look at the on-prem, we are achieving mostly the runtimes are in aggregate comparable to what you see on-prem. Also, for when we were initially populating the cache, we did not see a major impact from cache read operations. The compute phase was quite similar to what you would see in the cloud. And also the write phase between the S3 solution and the Luster did perform really well to meet the objectives of the workflow experiment we did here. So in all, we were able to run 2 levels of compute experiments with this architecture. One was physical design running at the core level, and the second was physical design running at SoC level. As you can see on the screen, we achieved approximately 12.8% average runtime per corner faster in both cases for core level as well as SoC level, leading into a maximum turnaround time of about 24.9% faster at the core level or at the full execution level. So this was basically successful execution of STA capability at both SoC level using primetime native tools, primetime and star RC from Synopsys. Also, we were able to demonstrate equal and or better turnaround time in the cloud, which was similar to on-prem. And data transfer rates were optimized with efficient caching solutions, because those of you who work in the physical design area would note that the data requirements for physical designs are way higher than other functional spaces. So having to deal with something like physical design with the data volume it drives was a very complex undertaking. But with the cache operations, it performed really well for us. So overall, any project that you take on has its architectural offerings as well as emerging technologies that you adopt in the process. But our key to success was also in the orchestration and process side that we implemented with engineering that made it even more powerful. So some of the areas we invested in was making sure we had full visibility on accounting and budgeting, because at the LSF level, if you put effective monitors and controls in place, then you are able to keep a very, very good watch over the budgeting pieces of it, which is obviously very critical to engineering as well as business operations, and saves you from having any surprises towards end of the execution plan. Also enabled interactive debug capabilities, which is very, very productive for physical design engineering, as well as areas where we could put monitors in place to reclaim the cloud instances when they were not in use or accidentally left over. And security, I mean, when you work in any Fortune 500 company, security is where your crown jewels are. You're dealing with red IP, yellow IP all the time. So we were able to go through a security governance process and gain sign-off for the architecture that we just shared with all of you. But also, I think the key is continuous oversight. It is a recurring process. So that is an area where we put very good governance on. So in all, sharing our summary, in our journey to AWS, we were able to enable hybrid cloud model for complex workload like STA. on a live design. We are very proud of everything we achieved as a team between us, Synopsys, as well as all the efforts from Amazon. That led to us demonstrating equal or better performance for complex EDA workloads in the cloud. So thank you to our partners in this journey for all your help in enabling Qualcomm, and look forward to working with you on doing even more with the rich team effort that we have going on with the ecosystem. Thank you very much.
Well, thank you very much, Anupama. That is super exciting to see, and it's been a pleasure to work with you and your team, and really looking forward to continuing that work. So awesome, and thank you again. So with that covered, we've covered and touched on a few things about the infrastructure, and of course this great example that Anupama has gone through. Let's talk about how you can actually enable your flows on AWS and some resources to be able to do that. So straight away, this is probably the best place to start. Just go out to this link. You're going to find all kinds of great information. This is a curated list of content that we're constantly updating. We have blog posts out here and white papers, reference architectures, starting from just some basic architectures to some much more complex. And I'll dive into one of those in just a second. But we also have more tools and training and much more content out here to include videos and other customer testimonials as well. So this is probably the best place to start and get you up and running quickly on AWS. Please reach out to your account managers, your solutions architects, anyone in AWS, and we'll be really happy to help you. So now this is a fairly complicated reference architecture, and we understand that. But what we're trying to really show here is the entire industry and the reach that AWS has across this industry. So in the top left there, you can see the on-prem data center talking about data and connections, and then in the middle you'll see the AWS portions, which include the infrastructure stand-up, so license servers and NFS servers and all of our native services that are there as well, to include FSx Luster and EFS, and of course S3 as well. So as we have customers that are actually transitioning over to AWS, we want them to think about how they can get a POC workload up and running quickly on AWS. So small set of data, something that they feel very comfortable with on AWS, and they see it actually work. And that's where we really try to get to first. But then we start building on that very quickly. Start thinking about, okay, well now let's actually extend that. Let's think about maybe actually converting an original S3 bucket into a data lake. And then how do you feed that into an analytics pipeline and into a QuickSight dashboard so you can actually start seeing how you can make better use of the data that you have, and you can actually reduce the time to market and increase your ROI. Another call out here about this diagram is the overall collaboration that you're going to see across the entire industry. In the bottom left there, you'll see the tool providers, and you'll see the IP providers as well. So let's think about how we can actually enable that collaboration across the third parties, but also with your foundry, right? So let's think about yield analysis and some of the wafer defect information. Does that potentially affect your design? If you're able to get that information quickly and while it's happening on the fab floor, does that maybe change your next design that you already have in flight, right? So we're trying to get our customers to think about the big picture and thinking about the collaboration across the entire industry. And this doesn't stop there, of course. Now you can talk about the contract manufacturers and devices themselves, right? Getting that feedback into collaboration, VPCs that allow your entire teams to collaborate across the entire industry. So although there's a lot going on here, we can walk you through this entire process, we can stand up this entire environment, and we're super excited to enable all of this across the entire industry, not just specific to an EDA flow, but also the IP libraries and the tools and the foundry data and all of this, and bring that all into one place so you can actually see and act on the data and the results from that data as well. And with that, I wanted to say thank you and really appreciate you attending this, this session. Again, very much appreciate everything that Anupama had done for this presentation, and really excited to continue working with her and working with Qualcomm. And thank you for attending reInvent. And don't forget to fill out your surveys, please. Thank you. Take care.